In this second video, the separate data we have is also the throughput data. So we're going to do a quick read of that and then also do the value counts. Here the value counts are going to be smaller because we had 3 machines and 3 days. So basically we have, for each machine, we have 3 days of measurements. For each day, day 1, 2, and 3, we have 3 measurements, 1 per machine. So let's do the same kind of analysis we did before. What we're going to do is do our plot of machines against throughput and machines against throughput. Okay, so we're going to do our cat plot of X is our machine and Y is our throughput. And just to show you why you might not always want to go with defaults, we have data actually here. I do want to change this to data, let's call it throughput, just so we don't accidentally override things if we go back to the top and look at other data. So data is data throughput. Okay. Now, this is the natural way to do box plots. That's great. That's fine. But what I want to highlight right at the beginning is that this is a bit of a lie. We have 3 data points. So these box plots are actually covering up the fact that there's only 3 data points, 1, 2, and 3. In fact, what we're going to do is just put both of these above one another, taking out the box plot here. And you see, there's only 3 data points. So the box plot would actually be deceiving in this case. It would be much more honest to simply plot the raw data itself when you have so few samples. The box plot is meant to collect a number of data points together and summarize it. Here, there's not much to summarize. So with that in mind, we're going to cover up the box plot and just look at the data plot. So what is this reading again? Throughput is the production level. So machine 1 produced 580, 595, 600 whatever widgets on day 1, day 1, 2, and 3 rather. Machine 2 produced more on some days, dramatically more, and then these other ones down here. But machine 3 consistently produced lower. This naturally leads us to the question, is this difference significant statistically? And my first thought, honestly, is that we have so little data, it'll be hard to get a statistically significant result, even with this graphical side showing such a clear drop. But let's take a look. So what we're going to do is borrow our whole one-way f-test here and put it down here. The difference is machine 1, 2, 3, that's right, except we want the throughput this time. And the data source is the data throughput data, so we have to be careful with this everywhere. And there we go. So we're going to measure 3 data sets, machine 1, 2, and 3 for their throughput, and then we're going to do the statistics one way, and we're going to do the same thing for the plot. Actually, we have the plot right here. Let's grab that. Again, it's nice to be able to compare the plot with the statistical analysis side by side. Okay, so there's our plot again, and here's our p-value. This is one of the classic examples of, oh, it's so close, and why cutoffs are problematic. Hard cutoffs in statistics are problematic. So let's put this back to a fixed point, and I'll even add an extra decimal there. So the p-value is 0.00055. So the null hypothesis, as always, is that all 3 throughput levels are the same on average across all 3 machines. What we get out of this is there is a, let's call it 55 in 1,000 chance of seeing the difference we see in the data. It means in the data, given the null hypothesis, if it's true. All right. Again, sales pitch wise, the machine operator, machine salesperson saying, you don't need to replace any of these things. Actually, that's a lousy motivator. Let's look at it from the view of the plant manager. So she has expenses to track and has other things she wants to spend the money on, doesn't want to replace any machines. These machines are all given the same throughput. There's no sense in replacing any of them because they're all about the same. Okay, well, that's their case. And then you come along and do this test and you find out, well, actually, if that's true, if all these machines are the same, I would only see this 55 times in 1,000 or 5.5 times out of 100. That seems pretty unlikely. What's the typical cutoff? 50 out of 1,000 or 5 out of 100. This is just a hair above that. What do you do? There's no hard and fast rules. This is where you come and bring your engineering expertise in and say, okay, that's a data point that seems suspicious. is there anything else I can look at that's separate from this? I'm not going to make this decision based on one p-value. I'm going to look at the whole situation now with that as one piece of the bigger puzzle and ask, would I replace the low performing machine? Would I replace the lowest performing machine? So we'll take a look at that. With that lens, then we can bring in the other information from earlier where we had the variability information as well. And so we'd say, well, there's evidence that machine 3 is worse from a throughput result. It's not totally convincing because we have relatively limited data, but there's evidence. Then we also have the evidence that the variability for machine 3 is high. And even further from the graphical analysis up here, that the variability by time of day, so this is the morning versus afternoons, morning shifts in machine 3 are much more variable than the afternoon shifts. And again, that points to if we were to replace one of the machines because our goal is consistency and high throughput, machine 3 would be the first one to go. So it doesn't have to come down to one statistical value. That collection of evidence across all the different spectrums and across the different goals gets you to what I would say was machine 3 would be the best candidate for replacement. I'm not going to put everything in here that we just said out loud in the interest of time, but the main things are it has the highest variability in general. It has the least consistent diameters at different times of day. And the other follow-up would be that it has the lowest throughput with some statistical evidence. Now notice these other ones are strictly graphical. We didn't actually do any statistical tests for this, so it's important to recognize that this is, I looked at pictures and this is what I saw. Again, that can be totally convincing, but it's worth noting that it's not the same as a statistical test. So with all that in mind, this would be the summary of the analysis of the data so far. In any real world scenario, of course, what your plan was and what your plan is after you collect all your data might differ. So it's worth mentioning that you would have alternative plans to immediate replacement. Again, if there's no burning reason to replace things today, then what you might want to do is test for 3 more days, get some more data. That might help to reinforce some of the statistical results. The other thing that I think would be on my mind anyway is if we're looking for variabilities, maybe it would be worth collecting more data and adding or learning about statistical tests for differences in variability. For the purposes of MEC 302, I will only ask you to apply the 3 tests we've seen: t-tests, chi-squared tests for proportions, and the ANOVA for multiple mean comparisons. But obviously there's a wide world of things outside of that. I would just ask you to think about what kind of tests would you look for and why as a follow-up to one of these kinds of case studies. As we wrap up the course, what I will be doing is providing some sample case studies, one for homework, one as extra practice, and giving you a chance to experiment with that before we get to the final test. As always, questions will be welcome via email or through office hours as we delve a little deeper into the more realistic applications of graphical analysis and statistics for engineering applications.